Good morning everyone, Mr. Simmons here. So I'm going to go through the textbook answers with you for topic P8.3 Resultant Forces. So after this topic you should know what a resultant force is, what happens if the resultant force on an object is 0 or is greater than 0, how to calculate the resultant force when an object is acted on by two forces acting along the same line, and for higher tier what a free body force diagram is. So study tip here, a common error is to think that when the resultant force on an object is 0 it must be stationary. It may just be travelling at constant speed in the same direction. Now this is something that you may well have overlooked, so I'm going to emphasise it as we go through the questions. So key points over here, the resultant force is a single force that has the same effect as all the forces acting on an object. So if you imagine there are lots of forces pushing and pulling on an object, but they overall add up to a single effect, and the resultant force is an imaginary single force that would have the same effect as all of those forces acting on an object. If the resultant force on an object is 0, the object stays at rest, means it's not moving, or at the same speed and direction. So if an object is moving and the resultant force on it is 0, it will carry on moving at that same speed and same direction that it was already moving in. That's actually called Newton's first law of motion. If the resultant force on an object is greater than 0, the speed or direction of the object will change, and Newton's second law actually spells out for us that the acceleration that it changes in is proportional to the force, the mass of the object. So we get the equation F equals ma, and we can rearrange that to work out that acceleration will be F divided by m, force divided by mass. If two forces act on an object along the same line, the resultant force is their sum if the forces act in the same direction. Now their sum means the forces added together. So in other words, if there's two forces acting along the same line, if you imagine a car being pushed by two people, the resultant force is the force of each person added together. If two forces act on an object along the same line, the resultant force is also their difference if the forces act in opposite directions. So the best situation to imagine this is a tug of war. So if the two teams are pulling in opposite directions, the resultant force is their difference. It's the force from one team subtracted from the force of the other. So if they both pull with the same force, the resultant will be 0. If one team is pulling with a bigger force, the resultant force will be acting in the direction that they are pulling it in. Then higher tier, a free body force diagram of an object shows the forces acting on it. So we're going to start off with the little kerboodle interactive that I've got for you here. I posted a link to this with the work, but the links for kerboodle don't always work, and if you're having struggle getting a link to open, then you can go in through kerboodle and you can open these interactives through the digital textbook, and I've posted up a video this morning as well to this channel showing you how to do that. I've sent out an email to you all with a link for that video. So which of these is the correct free body diagram for a submarine which is moving at a constant speed diagonally down to the right? Now the first thing you might be thinking is, okay, it's going diagonally down to the right. So if we look at this third one along, we've got an arrow pointing down and we've got an arrow pointing to the right. So the resultant of those two arrows would be going down there, somewhere like that. You might be thinking, well, there's a resultant force down there of those two arrows, therefore that would be the correct one. However, it says moving at a constant speed, and it's this moving at a constant speed which is the key to getting this question right. If it was this diagram here, if that was the correct one, well, that shows acceleration diagonally down to the right, not a constant speed. So again, if we look at this one here, so this one we've got the two arrows going right and down are bigger than the arrows going in the opposite directions, up and to the left, and therefore this would also have a resultant force going down in this direction, something like that. It wouldn't be as big as the other one. And so you might be thinking that that's the right answer, but again, if it's got a resultant force going down and to the right, it's going to be accelerating, not moving at a constant speed. So actually the correct answer is this one. You can see in this one all the arrows are equal in size, and therefore the object is going at a constant speed. So remember what it says in the study tip again: when the resultant force on an object is 0, it may just be travelling at a constant speed in the same direction. Okay, so to summarise that little answer at the bottom there, the submarine is moving at a constant speed, so the forces on it must all be balanced. Right, going on to the cyclist and the true and false statements now. I've put a couple of little pictures here just to help us to understand what's going on with the first statement. If the cyclist bends over the handlebars, they are reducing the air resistance. So if you look at the picture of the racing cyclist over here, they have various things that are streamlined to help reduce the air resistance. So their helmet is a nice streamlined shape. There are very few spokes on the front wheel and no spokes at all on the back wheel. These are all things to reduce the air resistance, but also because they are bent forwards over the handlebars, then that also minimises the surface area at the front of the bike and helps reduce their air resistance. If you compare with the much older picture down here, the cyclist from the 1920s, then you can see they are far less streamlined. They're sitting much more upright on the bike, and therefore they will have more air resistance, so they won't be able to go as quickly. The forces acting on the cyclist are balanced. So that one must be true because, as it says at the top, a cyclist is cycling at a constant speed. When the cyclist applies the brakes, there is a backwards resultant force acting on the cyclist. That one is true, so the effect of that will be to slow them down. Since the cyclist is moving, there has to be a resultant force acting on them. That one is false, because as we've already seen, anything can be moving at a constant speed even if the resultant force on it is 0. The thrust force is greater than air resistance. Well, if that was the case, then the cyclist would be accelerating, not moving with a constant speed, so that is false. If the backwards forces are greater than the forwards forces, the cyclist has to be going backwards. That's also false, because the cyclist can be going forwards, and if the backwards forces are greater than the forwards forces, they will just start to slow down and eventually they will come to a stop. So, question 1. Describe and explain what happens to the glider in figure 1 if the air track blower is switched off. So this is now questions from the textbook themselves. So there's the picture of the glider on the air track there from the book, and you can see the answer down here. The glider will make contact with the track. So if the air blower is switched off, the cushion of air that the glider is floating on will switch off. The glider will drop onto the track and make contact with it and stops moving along it. Friction is no longer absent. That's a wordy way of saying basically there's going to be friction now because it's dropped onto the track. It's not floating on a cushion of air anymore. When the glider makes contact with the tracks, so the glider stops because friction opposes its motion. So moving on to question 2. A jet plane lands on a runway and stops. State the direction of the resultant force on the plane as it lands. And you can see the answer here is opposite in direction to velocity. So the aeroplane is going in this direction. That is its velocity. And as it lands, there's going to be a force of friction between the wheels and the runway acting in the opposite direction. You can see the smoke there because that force is actually so great that the friction starts to melt the tyres and they start to smoke. So as it lands, that force of friction is going to be greater than the forward force of the plane, and therefore that's going to slow the aeroplane down to a stop. State the resultant force on the plane when it has stopped. Well, once it has stopped, there's going to be a zero resultant force on it. It's not moving, so there'll be no friction acting on it. And if there's no friction acting on it, then it can't have a forward force to balance that out either. So once it's stopped, the resultant force must be zero. So question 3, this is about the car stuck in the mud. A tractor tries to pull it out. The tractor pulls the car with a force of 250 newtons. Give the reason why the car does not move. And so you can see there the force of mud on the car is greater than the force on the car from the tractor. So that little symbol there is the mathematical symbol for greater than. So if you look at the diagram, the photograph to the right, so the tyres are in contact with the mud and there is resisting the force from the tractor. So as the tractor pulls in this direction, then the mud is pulling in the opposite direction, and the force of friction from the mud is greater on all four wheels added together than it is from the tractor pulling the car the other direction. Increasing the tractor force to 300 newtons, whoops, wrong pen. Increasing the tractor force to 300 newtons pulls the car steadily out of the mud at a constant speed and direction. Calculate the force of the mud on the car now. Well, there's not really a calculation to be done here. If it's going at a constant speed and direction, then that must mean that the resultant force is zero, and therefore the forces in opposite directions must balance each other out. Therefore, if it's being pulled with a force of 300 newtons, the force of the mud on the car, the opposite direction, must also be 300 newtons to balance that force and allow the vehicle to be moving in a constant speed and direction. Question 4a. Copy the car in figure 6 and show the weight of the car as a vector arrow midway between the wheels. So I've put here 4a, see blue arrow, so the blue arrow I've drawn there midway between the wheels and pointing downwards. Very simple. Then show the support forces of the road on each wheel as vector arrows. I put C green arrows here. So we've got the two green arrows acting upwards from where the wheel makes contact with the road. And I haven't measured this, but if I'd done it accurately, then these two arrows together would add up to the same size as the arrow pointing downwards, the weight, because the forces must be balanced. The car isn't sinking into the road, it's not going to go down, and it's not springing up in the air. Therefore the forces upwards and downwards must be balanced on it. So you can just see the mark scheme there for that. So weight vector downward vertical arrow with non-arrow end on the car midway between the wheels. That's what I've drawn in blue there. Support force vectors upwards and vertical from the point of contact of each wheel on the road. That's what I've drawn in green there. Okay, so hopefully this has helped you with this topic. Obviously, any questions, any difficulties, feel free to email me, and stay safe. And I'll see you again soon, hopefully. Cheerio.